This is the video tutorial for the speed of light activity. It is narrated and created by Sean Krupa and accompanies the Sound and Light lesson plan created by Jackie Haynall. This video and accompanying lesson plan are part of Ohio University's Ode of Knowledge in the Science Classroom funded by the National Science Foundation. The goal of this activity is to measure the speed of light using a microwave oven. Before you begin, make sure you have the following materials. One standard microwave oven. These can range in power from 700 to 1100 watts, but it's important to make sure that your microwave oven has a frequency of 2450 megahertz. You'll also need one microwave-safe plate, finely shredded cheese or another easy melting food, and a ruler or calipers. Before we begin, let's review some background on waves. The wavelength is defined as the distance between crests on a traveling wave. The frequency is the number of crests within a given window of time. Also, remember the fundamental relation between the speed of a wave and its wavelength and frequency. The speed is equal to lambda times f, or the wavelength multiplied by the frequency. Now let's review the electromagnetic spectrum. All of us are familiar with the portion of the electromagnetic spectrum we call the visible spectrum, or light. But light can have many other forms. If light has a shorter wavelength or higher energy than visible light, it's either an ultraviolet ray, an X-ray, or a gamma ray. If it has a longer wavelength than visible light and a lower energy, it's either an infrared ray, a microwave, or a radio wave. Microwaves are a low-energy wave with a wavelength on the order of centimeters. Remember that the velocity of all electromagnetic waves is the same, the speed of light. This is equal to 299,700,000 meters per second in air. Now let's talk a little bit about how microwave ovens actually work. Your microwave oven has a device inside called a magnetron. The magnetron is what turns the electricity into the microwaves. These microwaves leave one end of the device and reflect back off the wall. The pattern that is formed is called a standing wave, and molecules in your food are vibrated where the amplitude of the standing wave is the highest. For some of you, this may be the first time you've ever heard of a standing wave. Let's take a little closer look. Imagine that a wave leaves the left side of the microwave and travels towards the right side. When it reaches the wall, it bounces back and forms a perfectly overlapping pattern. Places with the largest area in between the curves are said to be the places where the amplitude is the highest. This is also where the food gets heated the most. In between places where the amplitude is highest are places where the amplitude is low or zero. These places would be cold spots because the molecules in the food would not be vibrated at all. As we just said, nodes cause the cool spots inside your microwave. This is why most microwaves have a turntable. The distance in between nodes is also the distance between points where the amplitude is highest, or the distance between cook spots. Because of the overlapping pattern, this is half the wavelength and not the full wavelength. Before going any further, make sure you can explain why this is half the wavelength and not the full wavelength. Now we're ready to begin the activity. To start, remove the turntable and the plastic piece that drives the turntable. Some of these come out easier than others, so it might be a good idea to have a flathead screwdriver nearby in case you need to pry it out. Next, spread a thin layer of shredded cheese over the microwave-safe plate. It doesn't have to be a perfect layer, but you should spend some time making sure it's as even as reasonably possible. Next, microwave the plate for 5 to 10 seconds on the highest power and let it cool for a few seconds afterwards. You should be able to see spots where the food has cooked and spots where it looks like nothing has happened. Identify the cooked spots and, for convenience, give them labels. Next, taking your ruler or calipers, measure the distance between adjacent cook spots. This can be a bit of a judgment call, so it's recommended that you do the following. Move to one edge of a cook spot and measure the distance from that edge to the nearest edge of the adjacent cook spot. This should give you the most precise results. Create a table for your data and average all your measurements. In the example, we got an average distance between cook spots of 6.2 centimeters. You can now use Excel or a calculator to determine the speed of light using your data. Remember, we said that the speed of light is equal to the wavelength times the frequency. We also explained that the average distance between cook spots would be half the wavelength. Therefore, if we take 2 times our average distance in meters and multiply it by the frequency, 2.45 times 10 to the 9 hertz, we get the speed of light. For the example data, we calculated the speed of light to be 3.045 times 10 to the 8th meters per second. In order to make a determination about how good our calculation was, we should calculate the percent error. For the sample data, the percent error was 1.6%. Finally, include a table of all your measurements, results, and analysis. Here's a summary of the points that we covered. Using a standing wave pattern in a microwave oven, the speed of light can be measured experimentally. Hot and cold spots in the food are separated by a distance of half the wavelength apart. For a fun expansion of this activity, you might want to try different materials. Chocolate chips, egg whites, another form of cheese, or other easy melting foods might be a good choice to try. This concludes the video tutorial. Thanks for your attention.